Okay, so we have talked about two examples of LP formulations. The last thing we want to tell you is about compact formulations. This will be required for big problems. So most problems in practice are of large scales. Okay, that means the number of variables and the number of constraints are really huge. And if we still use the old way for formulating problems, then we need to write too many things down. Okay, so compact formulation simply means we want to group constraints and variables so that make the formulation compact. We know many variables can be grouped together. For example, the production quantity of each day can be grouped into one single sentence, right? You don't need to write 4 lines and repeat a lot of things to define 4 production quantities. And also constraints can also be grouped, right? For all those non-negativity constraints, we have already done so. So today, I need to give you another example to show you that how may we compact, make other things compact. So essentially what we need are the following 3 things. We use indexes, summation, and the for all operator to make our formulation easier to read and to group variables. Okay, so let's see how may we do them based on how may we do so by using the inventory problem as an example. So the problem we mentioned is that we have 4 periods, right? We always produce and then sell in each period. Unsold products can become ending inventory, and we want to minimize the total cost. Okay, so that was our problem. Now I want to do compact formulation. So the first thing is to decide what's the indexes I want to use. In this problem, what is repeating are periods, right? So things are repeated in each repeating in each period. So certainly we want to group items, group things according to periods. So we're going to let T from 1 to 4 as the index for periods. If you are producing multiple products and they all have some similar properties, you are going to use, for example, I to be the index of products. Or for example, you have multiple resources, then maybe you will use index J for resources. Anyway, here we only have one product. There's no resource whatever. So we use T to be the index for periods. And then my objective function. Okay, let's see this. Originally, I have 8 terms here, right? But why should I do that? I can just combine the last 4 terms into one single term with this summation. Moreover, if I call this unit cost on day T, I give them a name CT, then the whole thing here is nothing but one single summation, right? For T is 1, I am doing 9x1 plus y1. For T is 2, I am doing 12x2 plus y2. And this summation gives me the 8 terms here. Okay? So when I have something that are meaning the same thing in different days, I can give them a single name with index to represent all of them. Okay? Just like what we are doing for variables. So by doing so, I can simply use this as my objective function. Also, we can group constraints. So all the 4 constraints somewhat look similar, right? So let's do this by grouping the 4 inventory balancing constraints. Let's call this 100, 150, whatever, as DT as our demand, daily demand. Then for day 2 to 4, I can use one single expression, yt minus 1 plus xt minus dt should be yt. Here, yt is the ending inventory of day t, so yt minus 1 is the beginning inventory, and then dt is my demand. So the ending inventory plus what I produce minus what I sell is my ending inventory. One important thing is that you cannot say this expression is for t from 1 to 4, because at day 1, if you say t is 1, you get y0. Okay, but y0 is undefined, so you cannot do that. You can only say that I have this for t from 2 to 4. You cannot say from 1 to 4. So certainly that's not very satisfactory. So let's do this. I want to group all of them into one expression. So I am going to add one additional decision variable called y0. Again, I still call yt as the inventory, ending inventory of day t, but now this expression comes from 0 to 4. It's something like you are expanding the size of this set of decision variables. Okay? Previously, t is from 1 to 4, but now t is from 0 to 4. You have 5 inventory variables. And then the set of inventory balancing constraints can be combined into one single sentence, right? Because now you can write t from 1 to 4. So certainly there's one thing you need to do. You need to set the initial inventory. Okay, initially you have actually 0, and you need to set y0 is 0. In many situations, you actually have some initial inventory, and then by doing so, you can write down the initial you can include the initial inventory in your formulation. So our compact formulation is here. Okay, I want to minimize this with a summation to combine all those terms inside the objective function, subject to one single sentence, one inventory balancing constraint for all t from 1 to 4. All those non-negativity constraints for all t from 1 to 4, and y0 should be 0. Okay, by using for all, I do not need to write 4 lines for these inventory balancing constraints. One important thing that I want to remind you is that this for all modifier is really required. Okay, you cannot simply write something like this without a for all statement. If that's the case, we do not know what are you indicating for, okay? And that formulation is just wrong or incomplete. Okay, if you do not have this, there must be some points taken off. And then non-negativity constraints for multiple sets of variables are typically combined together. Officially, you should write xt greater than or equal to 0, and then yt greater than or equal to 0, but that's too tedious, right? They are just non-negativity. So typically, we write in this way. One additional convention that I typically use and I suggest you to use is to use lowercase letters for variables, for example, small xt, but use uppercase letters for parameters, for example, capital CT. The reason for doing that is when I look at a formulation, immediately I can see these are parameters, but other things, x, y, whatever, they are variables. Okay, so it helps me to understand the formulation. Also, it may help me check whether I am making a nonlinear program. For example, if I have a product of decision variables, then that's nonlinear, right? But I can certainly have a product of decision variable and parameters, or product of parameters. That's all fine. So by setting them to be lowercase and uppercase, I can very quickly check whether I accidentally make two variables multiplying each other, or so on. Okay, my suggestion. Not everybody are using this, but that's my suggestion to you. Okay, so we mentioned something about parameters, so let me say more about it. When we are creating parameter sets, we typically write something like this. Okay, I'm going to call CT as the unit production cost, blah blah blah, whatever. First, you don't need to write down those values as they are actually given in the problem. Okay, but you really need to write one line like this to clearly declare that CT is the name you're going to use for unit production cost. This statement must be as clear as what you are doing for defining variables. Okay? Also, you need to specify the range through indexes. This T from 1 to 4 is also required, just as those for all statements. Otherwise, no one knows what are you talking about for small t. Okay? Parameter declarations should also be put at the beginning of the formulation. Again, before you use something, you need to tell us what is that. Okay? Just as what you are doing for decision variable. Parameters and variables, they are certainly different. Variables are those things that we are going to decide. We do not know those values before we solve the model. But the parameters are given with known values. Okay? It's important for you to understand in your formulation which part are variables and which parts are parameters. Okay? Only if you have a clear idea about that, you may write correct programs. Finally, parameters are called exogenous and variables are called endogenous. So when you read these two terms, that means, oh, something is endogenous, that means something going to be determined, something may change, that are variables. If something is exogenous, that means that are given or fixed. Okay? Okay, so that's the end of the introduction of linear programming. We gave you some basic terminology, basic idea, basic properties, what's the classification of linear programs, how do we graphically solve them, why an extreme point is related to optimality, and some examples about formulation. So in the lecture, we're going to do some more discussions, and in the next lecture, I'm going to tell you how to solve general linear programs. Okay, thank you.